Today we shall start our lecture with the free particle, and then we shall study a particle trapped in a one-dimensional infinite potential well. So first we study the free particle. One of the simplest applications of the Schrödinger equation is found in the treatment of a free particle. By a free particle, we mean a particle of mass m not subject to the action of any force. That is, the potential energy is zero. The potential energy is zero. And the total energy is therefore entirely the kinetic energy. The Schrödinger equation in this situation takes the following form. Where E is the total energy and here the entirely the kinetic energy of the particle. Now the solution of this equation, this is the Schrödinger equation. Of course, it is time independent Schrödinger equation. The solution, there are two solutions because it is second order partial differential equation, and the solution is written as one solution is say constant amplitude here c1 e to the power I k dot x, where x is a three-dimensional position vector that contains x, y, and z, and a second solution c2 to the power minus I k dot x, where x is x, y, k is known as the propagation constant, or propagation vector, and its magnitude will be given by this. Okay, now you see there are two solutions, and from this the propagation constant k can be written as this. In one dimension, we have the Schrödinger equation, and the solution will be let us say the one dimension is along x direction, this. For the probability of finding a particle to remain finite as x goes to infinity, the necessary condition is that the energy E, this energy E must be positive. Otherwise, if E is negative, then the first term, this term, if E is negative, then this K will be imaginary, and that will give you e to the power minus kx, and as x approaches minus infinity, then this term goes to plus infinity. Similarly, this term will go to infinity when x tends to infinity. And we know from the first postulate of quantum theory that um, the wave function must be finite everywhere, including at the boundaries at x equal to minus infinity or x equal to plus infinity. Therefore, our condition we'll have to impose here is that the energy must be greater than or equal to 0 for free particle. Under such restrictions, the arbitrary constants, this C1 and C2, can now have any values. Therefore, for a free particle, energy is not quantized and it can have any value greater than 0. And the energy spectrum will be continuous, not discrete. The conclusion is in agreement with the observed spectra of an atom. The dissociation of an electron from the atom and the radioactive emission of alpha rays and beta rays are some of the examples of free particles, provided that there are no interactions of these particles with any other particles in the universe. In fact, the free particle problem represents an unreal situation. Classically, the waves associated with the free particles are progressive in nature. That means traveling waves. Okay, this is for free particle. Now we shall discuss about a particle trapped in one-dimensional infinite potential well, and we shall discuss this in detail. We shall find the wave functions, a wave function of the de Broglie wave associated with the particle trapped in the one-dimensional infinite potential energy, and we shall also find out the energy, possible energy of the particle trapped in the potential well. Okay, a particle trapped in a one-dimensional infinite potential well. Okay, this is minus infinity, and the width of this well is say a. So this in this region, the potential energy is 0, and from 0 to a, potential energy is minus infinity, and from a to plus infinity, the potential energy is again 0. So if a particle inside the potential well, then it will have a de Broglie wave, and the wave will be bounced back from the walls of the potential well. Now, the particle is trapped inside the potential well, so we do not need to consider the Schrodinger equation outside this potential well. So the range of our differential equation, that the Schrodinger equation we are going to solve, so will be confined in the region 0 to A. But our problem is, if we write down the Schrodinger equation, and the potential energy, this is this is infinity, so is okay. This equation we cannot solve. So to overcome this problem, we draw an equivalence equation. Okay, so here now the potential is plus infinity outside this oil, and inside this, from 0 to A it is 0, potential energy is 0. And so if this is the axis, we draw the potential energy, and this is infinity, this is also infinity, but here the potential energy is 0. The particle is still trapped inside the potential well, but this situation is an equivalent situation of the previous case. And here, if you want to solve the Schrodinger equation in the region 0 to A, now the potential energy is 0, so we have no problem here. Now the solution of this equation can be written as this. Remember, we are solving the Schrodinger equation in the region 0 to A, because outside this region the potential energy is infinity, and the particle cannot be found in those regions. Now we apply the boundary condition. So our first boundary condition is at x equal to 0, our wave function must be 0. And second boundary condition is also at x equal to A, the wave function must be 0, because the particle cannot go out from the potential well. So if we apply these boundary conditions in this wave equation, we should write down here the wave vector. Wave number is k square equal to 2me by e square. K is the propagation vector, and in one dimension we do not put the vector sign, so you can say this is propagation constant given by in terms of the energy of the particle. So this boundary condition 1 gives us 0, since cos 0 is 1, so this is equal to a plus 0. So this one gives us a equal to 0. So the solution can be written as b sine kx. Now the second boundary condition, second condition we apply. So 0 is okay. Now sine k into a when x is equal to a. But you see the product of two factors b and sine of k is 0. So, but b is not 0, because if b is 0 then we will have no solution. Therefore sine k is 0. And this can be written as sine n pi, where n is 1, 2, 3, dot, dot, dot. 0 is excluded, because if n is 0, then this always the solution will be 0. So from this ka equal to n pi and k equal to n pi by a. So the wave number, the wave number is not continuous, it is discrete. Propagation constant k is known as the wave number, is discrete in nature. Okay, if we substitute this k in this wave function, and also here, then we get solution b sine kx. So k is n pi by a, and since this factor depends on n, so we put a subscript n on the wave function. And similarly, if we put k equal to n pi by a in this propagation constants expression, so we have n pi by a whole square equal to twice m e by a square. Since this depends on n, so depends so you put a subscript n. From this you can show that en is given by this. So we see the wave function and the energy both are discrete in nature. Now we'll have to find the normalization constant. Okay, normalizing psi n. So our normalization constant is if the normalization constant is b, then we have here the modulus of psi n square. Integration of this is 1. The limits are minus infinity to plus infinity, but our limits will be 0 to a. So if you substitute this, and this one will give you b square is sin square n pi x by a dx is equal to 1. It's easy to integrate if you divide by 2 and you multiply here by 2, and the twice sin square theta. Here you can put the formula 1 minus cos twice theta, and you can easily integrate this. And if you integrate this, you will find and you will find the constant b equal to square root of 2 by a. Therefore, the wave function and energy of the particle trapped inside the one-dimensional infinite potential well are this. B, instead of b you put this sin n pi x by a, and the energy is En, which is equal to n square pi square h square by twice ma square. Okay, now we can plot this wave function and energy. We consider where n is 1, 2, 3. These are known as quantum number. Okay, we want to plot few wave functions and energy. This is 0 to a. Let us suppose that this is a for n equal to 1. We can call it a ground state. N equal to 1. Here n equal to 2. Here n equal to 3, and so on. When n equal to 1, we have psi 1, which will be square root of 2 by a sine pi x by a, and the energy E1 will be pi square square by 2ma square. Here psi 2 will be square root of 2 by a sine, so twice pi x by a, and energy E2 will be 4E1. Because this is 4E1, because if you put n equal to 2, then it will be 4, and this is actually E1. Similarly, psi3 will be square root of 2 by a sine 3 pi x by a, and E3 will be 9E1. So in terms of ground state energy, E1. And if you want to plot this function psi1, it will be like this. If you plot psi2, it will be like this. This is psi3. Okay, and similar to this, you can continue. The ground state energy here we call it E1, and this is pi square a square by 2m a square, where a is the width of the one-dimensional potential well, and this energy is known as 0-point energy. This ground state energy is known as 0-point energy. Therefore, the position of the particle cannot be precisely known. This shows that the particle inside the box is not at rest even at 0 Kelvin. In such a situation, only the mean value of the kinetic energy can be determined, and therefore the momentum of the particle is also not known precisely. The occurrence of such a 0-point energy is therefore in accordance with the Heisenberg uncertainty principle. Further, it is apparent from the energy expression, this one, that the bigger the box means we increase A, and behavior particle, the lower will be its kinetic energy. Here the energy is entirely the kinetic energy because inside the box potential energy is 0, and more localized its motion, the higher will be its kinetic energy. We can show that the wave functions, they are orthogonal to each other. Different excited states. Are orthogonal to each other. This is a theory. That is, if psi m and psi n are the wave functions, of two different states, that means when m is not equal to n, then the inner product of psi m and psi n will be 0. And the inner product of two wave functions is 0. That means the wave functions are orthogonal to each other. So this actually we can write down as 0 to a, and this is complex conjugate in the one dimension, which is equal to 0 for m is not equal to n. If we want to prove this, then we write down psi m and another is psi n, therefore the inner product of this psi m and psi n will be so if you substitute these two, this is a real quantity, so asterisk complex conjugate is the same as the function. Okay, now this one can be written as 2 sine a sine b. It is cos a minus b minus cos a plus b. So if you assume that this is a and this is b, then cos a minus b, so will be pi by a, this, and minus cos a plus b Okay, now if we integrate this, so we'll have 1 by a, and so is pi by a m minus n. This will be sine Okay, now if you substitute this, but we know that m is not equal to n, so the denominator, this m minus n or m plus n, this is non-zero. That means an integer, positive or negative. Now if you substitute the limits, you see m minus n is an integer, m plus is an integer, if you put this a here, so a will be cancelled out, so the argument will be some integer multiplied by pi, which is 0, and sine 0 is 0, so this term gives you 0. Similarly here, when you put this upper limit a x equal to a will be cancelled out, and m plus n is an integer, so sine pi into integer will give you 0, so we get 0. Therefore, the inner product of psi m and sine is 0, showing that psi m and psi n are orthogonal to each other for m is not equal to n. Yeah, okay. So this is for today. We shall stop here, and in the next lecture we shall discuss about potential barrier. That means when the potential energy is positive, and in particular we shall consider a single step potential barrier.